Well, thank you very much. I really appreciate this, and so it's a big honor for me when Professor Najafi called me to let me know. I was thinking that, sure, there are so many good graduates of Michigan that were students here at the time that I was a student, so it's a very big honor for me to be selected to receive this award. The other thing that I'd like to mention is that so I've been fortunate, I've had quite a bit of success, and I'm grateful for that. But none of that would have been possible without being in the right conditions. So, so the education that I received here in the University of Michigan, that was instrumental. And I credit Professor Sarabandi to a great extent in making that happen. So he helped me get admission here, and then was a mentor that gave me freedom to do research on a lot of different things that were very helpful, and also the colleagues that I have at the University of Wisconsin. So, so you hear these things in the bios that, oh, these people have had such and such success, and they've received so many awards, and you may think that oh, they've been all individuals that have done that individually, and in my case, it has definitely not been the case. So the environmental conditions have been instrumental in making that happen, and I'm very grateful for that. So having said that, I'd like to start my presentation. So the title of this talk is High-Frequency Microwave Ablation Antennas for Minimally Invasive Treatment of Cancer. And I'd like to actually start this presentation with this slide. Yesterday I was meeting a couple of people, and they were asking me questions about Wisconsin. They were asking me certain questions that I did not know the answer to. I was actually pretty embarrassed. So early morning, I added this slide to my, my presentation. So UW-Madison, is in Madison, Wisconsin, obviously. Madison is the capital of the state of Wisconsin. It's a very beautiful city. It's between two big lakes, and this is sort of the aerial view of our campus, and this is Lake Mendota and Lake Monona. And downtown is actually between these two lakes, and our campus is by the southern shore of Lake Mendota. So in the spring, it's really, really nice, and in winter, you know how winters look, in the Midwest, but it's still, it has its own beauty. So the university was founded in 1848. We have 13 schools and colleges, and we have more than 40,000 students, about 9,000 graduate students, 20,000 faculty, and more than 400,000 living alumni. I think Michigan has something like 500,000 plus living alumni. And it's a pretty big university in terms of research. So I think in the United States, there's Johns Hopkins, Michigan, and then Wisconsin in terms of R&D expenditure. So in many aspects, it's a very similar environment to Michigan. It's a Midwestern town, a very interesting college town. And if you haven't had a chance to visit Madison, I definitely encourage you to stop by. The other thing that I'd like to say before I start any discussions on our research activities is to give acknowledgement on the work that my past and current students and postdocs and collaborators and my collaborators have done. So I'll present a lot of results there, and this is pretty much the work of all of these past students and postdocs, the current students, and also many collaborators that I have, and the funding agencies that have supported this work, without which we would not be able to do any of this work. So as Professor Najafi mentioned, my research area is in the applied electromagnetics area, and the core of that work is on antennas. But over the years, we have expanded to different areas. And so this slide shows kind of a highlight of the different areas that we work on. And in the next couple of slides, I'll actually show very small samples of the projects that we have in each of these different areas. So, I did my PhD on small antennas, and that's an area that we are still working on, designing compact broadband small antennas at low frequencies, or, at high frequencies, antennas that are physically small. That's a very challenging problem that we are still dealing with. And so we have a couple of projects in that area. In the area of periodic structures and metamaterials, we are working, and that's again something that I started at in my last year at University of Michigan, and we continued that. In that area, we're looking at concepts that can be used for designing high power or affordable phased array antennas. But over the years, we have also branched out to look into the intersection of problems that are at the intersection of electromagnetics and other fields. Now, the E&M area is a very mature area, so there's not a whole lot of problems that remain unsolved, but there are a lot of interesting problems that are at the boundary of electromagnetics and other disciplines that you can solve by collaborating with scientists in other fields. And in that area for us, we are looking at some problems in the millimeter wave infrared systems, some biomedical application problems, some problems in the high power microwaves area, and in the wireless communication applications. So these are some samples of the projects that we have in the electrically small antennas area. So as I mentioned, we are looking at problems involving designing electrically small antennas, either for wireless communication applications, for military communications applications, or for direction finding. So these are some of the pictures from some projects, individual projects that we have in these areas. We're looking at small antennas that work at HF, VHF frequencies for military communication applications. For example, in this case, we are looking at the possibility of using an entire vehicle as the antenna, and what we call as the antenna as a mechanism to excite currents in the vehicle itself. Some direction finding concepts, antennas that are based on the auditory system of small animals, again for direction finding. And so all of these problems are problems that deal with addressing the fundamental challenges of electrically small antennas. In the periodic structures, we are looking at, the fundamental problem that we are looking at is this problem of affordable phased array antenna technology. So phased array antennas are out there, a lot of phased arrays have been deployed, but the problem is that, these are very, very expensive, and only the most expensive pieces of military hardware can actually afford to use phased arrays. But there are many other applications that can benefit from using phased arrays. And in this area, we're looking at, sub-wavelength periodic structures that are made tunable, and we're using these in designing wideband microwave lenses and reflectory antennas that can be used in turn as part of a phased arrays. And these are some of the samples of different activities that we have done in this area. Going to higher frequencies, if you think of electromagnetic waves and Maxwell's equations, Maxwell's equations are valid at whatever wavelength that you're looking at. And so you can take a lot of concepts that we have worked on at the microwave and RF frequencies and scale them to millimeter wave and infrared frequencies. And we have been doing a little bit of that. So for example, we are looking at some of these direction finding antennas that we have designed at UHF frequencies. We have taken these concepts, taken them to infrared frequencies. At the long wavelength infrared band, we are designing infrared detectors that are sensitive to the angle of incidence of the infrared light, or can sense the polarization of the wave. And the idea here is to design detectors that can extract additional information from an incoming electromagnetic wave beyond the irradiance of the wave that's normally measured in conventional optical detectors. Again, some of the frequency selective surfaces that we have designed, we're building terahertz and infrared filters based on those as well. The biomedical applications, that's an interesting area. We sort of branched into this 5-6 years ago or so. And in this area, we're looking at two different types of problems, diagnostic problems and therapeutic problems. So I'll talk about microwave ablation, which is the subject of this course, which is a therapeutic problem or application of microwaves. But we're also looking into new techniques for doing medical imaging. One interesting thing that we're working on is this concept of electron paramagnetic resonance imaging system. So EPRI systems are very much like MRI systems, but rather than imaging protons, they image electrons. And because of the smaller mass of electrons, these systems work at much higher frequencies. So essentially, designing EPRI systems is very much like designing any other RF and microwave circuit that we design, but the application is medical imaging. And over the past couple of years, we actually have put together a home-built EPR system, a spectroscopy system, and we're in the process of actually converting that to an imaging system. So that would be like a very low-cost alternative to MRI for high-resolution medical imaging, in vivo human imaging. In the high-power microwaves area, this is another interesting area, because what we are doing in this area is, the field of high-power microwaves and plasmas, it's a very old field. Electromagnetics is also a very old field. But if you look at the boundary, at the intersection of these two fields, there are problems that you can work on, which take some concepts from electromagnetics, take some concepts from high-power microwaves, and basically solve problems that have been long unsolved. And in one of these cases, we are looking at this concept of metamaterial enhanced resistive wall amplifier. So this is a vacuum electronic-based amplifier where where you can essentially get really high gain values and extremely high power levels out of this amplifier. We were talking about gigawatt levels of powers over pretty broad bandwidth. And this basically works by designing circuits that enhance the interaction of an electron beam that's propagating in vacuum with a metamaterial-based circuit that essentially enhances, the interaction of electromagnetic waves with electron beams. And so we have a project in that area, and we're building prototypes of these amplifiers. Looking at some other concepts, new cathode designs, breakdown in metamaterial structures, multi-packing concepts, and so on, are as well on our to-do list. And finally, in the wireless communications area, one of the problems that, as a nation we are dealing with is this problem of finite electromagnetic spectrum. So some of you may know that NSF has this program called Enhancing Access to the Radio Spectrum, and the goal of this program is to basically come up with technologies that can enhance the access to the radio spectrum, basically make us use this available spectrum more efficiently. And so in that area, we are actually working on 2 projects. Both of them are funded through this EARS program. And the idea in each of these is to come up with systems with wireless communication architectures that use innovative antenna designs where, where in the wireless communication systems and these antennas work in concert to essentially enhance the efficiency of a spectrum usage. In one case, we are looking at millimeter wave communication systems that use reconfigurable antennas for MIMO communications at millimeter waves. In the other case, we are looking at relatively low frequency UHF, VHF MIMO communication systems that use directional small antennas for enhancing the efficiency of spectrum usage. So these are some of the samples of the projects that are going on in my group. There's no shortage of exciting ideas that we are working on, and if any of you are interested about any specific thing, I can talk to you about these after the presentation. But what I want to do right now is to focus on the main topic of this presentation, which is this concept of high-frequency microwave ablation for minimally invasive treatment of cancer, and that's the subject of one of our projects. So what is microwave ablation? Basically, it's a thermal therapy of cancer where what you do is you introduce microwave energy into a tumor and basically heat the tumor from inside, raise the temperature to really high levels, 50, 60 degrees centigrade. And after that, once the temperature is raised beyond that, the cells start dying off immediately. And, that's sort of a radiation therapy, but it's non-ionizing radiation therapy. So conceptually, it's shown here. You generally have an interstitial antenna that's placed percutaneously, inside the tumor, and using some sort of a microwave source, you introduce the energy into the tissue and start basically heating the tissue from within. Now, this concept has been around, and people have been working on this for many years. And conventional wisdom was that in order for this to be effective, in order for microwave ablation to allow you to get reasonable sizes of ablation zones, you have to use relatively low microwave frequencies. Basically, low microwave frequencies means around 900 megahertz or 2.45 gigahertz, and that's basically the majority of studies. Those are the frequencies that the majority of studies had used. And the idea was that because the wavelength of electromagnetic waves is larger at these frequencies, the penetration depth would be larger, and that allows you to get larger ablation zones. Now, in one of our studies, we're coincidentally looking at some implanted antennas that were working at much higher frequencies. And we were looking at thermal effects of these, and we saw that this was not true. We were actually getting similar heating zones and heating patterns from these high-frequency antennas compared to low-frequency antennas. So that prompted us to look into this a little bit more, and we basically said, okay, let's examine doing microwave ablation at low microwave frequencies versus high microwave frequencies. And our simulation results kind of indicated that there should be no major difference, and we set out to do an experimental study. So what we did was to do a comparative study where we designed microwave ablation antennas at 2 different frequencies, 1.9 gigahertz as a representative of a low frequency for microwave ablation, and then 10 gigahertz as a representative frequency for high frequency microwave ablation. And the antennas that we used are shown here. These are previously reported microwave ablation antenna where what we have is a coaxial cable feeding a dipole. This is one arm of the dipole. The other conductor of the coaxial cable forms a second arm of the dipole, and then we have a floating sleeve there that uses as a choke or as a balun to cut off any electric current that you have just flowing on the other surface of the other conductor of the coaxial cable. So basically with this balun, what you get is a dipole antenna fed with a coaxial cable, and these baluns, by the way, are a general fixture of all these microwave ablation antennas that are fed with coaxial cables. So we designed two versions of this antenna working at 1.9 gigahertz and 10 gigahertz, and we started doing some simulations, both electromagnetic simulations and combined electromagnetic and thermal simulations. And what you're looking at here is the SAR pattern. SAR stands for a specific absorption rate. Basically, that gives you the amount of energy that's absorbed inside the lossy tissue. And what you're looking at is the SAR patterns of these two antennas. So this is the antenna at 10 gigahertz, and this one is the one at 1.9 gigahertz. And clearly, you see that, let's say if you take these negative 25 dB contours, you see that this is a smaller. So the scales here are from 8 millimeters to negative 8 millimeters, so roughly 1.6 centimeters or so, whereas the 1.9 gigahertz antenna has a very larger SAR pattern. So this was the basis for all the previous studies claiming that lower frequencies would be more efficient because you get larger SAR patterns, and people actually had not looked at the higher frequencies. But SAR pattern doesn't tell you the whole story. It basically tells you, it defines the region where you're depositing most of the electromagnetic energy. So then we did some thermal simulations. You can use the SAR pattern, the energy that's deposited in the tissue from your electromagnetic simulation, as a source of a transient thermal solver, and basically look at how the ablation zone grows as a function of time. So what we are looking at in this figure are the boundaries of the ablation zone defined by the contour level where the temperature, the 60-degree contour level. So inside this volume, inside the contour, the temperature is higher than 60 degrees. Outside of that, it's below 60 degrees. And at 10 gigahertz, you see that, as we increase the time from 0 to around 10 minutes or so, the ablation zone increases, and the two different curves that you see there, the black and the red ones, they represent the ex vivo and the in vivo cases. The ex vivo case is for a dead tissue where there is no blood perfusion, and the in vivo is for live tissue where you have the cooling effects of blood perfusion. And well, in both cases, you see the ablation zone growing, and not surprisingly, the ex vivo ablation zones are larger than the in vivo cases. And if you do the same simulation for the 1.9 gigahertz antenna, you do see a similar trend, basically, that the ablation zone increases in size and the ablation dimensions for the in vivo case are smaller than the ex vivo case. But when you do compare them side by side at the same time, you see that the ablation zones, like at the earliest stage, at 10 gigahertz, you start having heating faster. So for example, at 10 seconds or so, we already have an ablation zone established here, whereas we don't have here. And at 1 minute, the ablation zone here is larger than the other one. And if you look at some late time stages, at 10 gigahertz and 1.9 gigahertz, then we'll see that that the ablation zone dimensions are actually comparable at both the 1.9 gigahertz case and the 10 gigahertz case for both the in vivo and ex vivo cases. So these simulations, yes?
Is the antenna the same? So it doesn't seem to be scaling with wavelengths, right?
No,
and it's not 5 times larger.
Yes, that's a good question. The antenna design is the same, but your dielectric constant actually is very dispersive. So your dielectric constant is much higher at the 1.9 gigahertz compared to 10 gigahertz. So it's not exactly 5 times, right? But yeah, so so the finding from the simulation results is okay. You should get similar ablation zone dimensions, but then you have to do experiments. You can do all your simulations, and nobody will believe your simulation results until you have measurement results. And so we did some basic ablation studies. We did 16 experiments in ex vivo bovine liver. So this is the ablation experiments, we did 8 at 10 gigahertz and 8 at 1.9 gigahertz, and for 2 time durations of 5 minutes and 10 minutes. So we actually had fabricated antennas and used the antennas for these different ablation experiments. And what we are looking at here is some measurement results of the input VSWR of the antenna for before and after ablation. And you can see that at the frequencies that we did our experiments, for the 1.9 gigahertz antenna, In both cases, we maintain our impedance matching for before and after ablation. So what that tells us is that during the ablation process, even though the dielectric constants of the environment is changing, the input impedance of your antenna doesn't change significantly, doesn't change enough to deteriorate your impedance matching so that your effective total power is different. So the other thing that we did during the experiments was to monitor the temperature within the tissue at different locations along the antenna. So what we have here is our antenna for the 1.9 and for the 10 gigahertz case, and we have a fiber optic temperature measurement system that has 4 channels, and we basically put 3 channels in the plane perpendicular to the antenna, and 1 channel in the plane away from the tip of the antenna. So this channel 4 is actually away from the tip of the antenna by 1 centimeters, and channels 1, 2, 3 are 5 millimeters or away from the cross-section of the antenna by 5 millimeter distances. And so in the next couple of slides, I'll actually show you measurement results of the temperatures, and that's very interesting as well. So when we do the experiment, the ablation experiment, the temperature levels that we get are like this. So for example, for the 1.9 gigahertz, so remember that channels 1, 2, 3 are in the plane perpendicular to the antenna, and channel 4 is in the plane along the longitudinal axis of the antenna. We'll see that in these cases, basically the temperature levels start increasing, and it kind of makes sense that channel 1, for example, which is closer to the antenna, temperature is higher, and 2 and 3 are lower, and they both increase kind of roughly at the moment that we start applying microwave power. For the 10 gigahertz case, though, the other thing is that in these experiments, whenever the temperature exceeded like 110 degrees or so, we actually removed removed the probe, because that was the maximum temperature that the probe could tolerate. So if you see this cut off, it's because of that. For the 10 gigahertz case, this is also interesting. If you look at this, for the 10 gigahertz case, the channel 1, which is like 5 millimeters away from the antenna, the temperature rises up very rapidly, and before 1 minute or so, it's above 100 degrees C. And channels 2, 3, 4, for about 20 seconds, they don't register any rise in temperature. And after that, we'll see the rise in temperature. And that's interesting because it essentially tells us that the moment that we start applying electromagnetic power, there's not much heating going on in channels 2, 3, 4, and this happens with a delay. And what turned out to be the case was that at higher microwave frequencies, as I showed a little bit earlier, the antenna generates a much smaller SAR pattern. So the antenna deposits its energy in a much smaller volume, and this smaller volume is where the first heating starts to happen, right? And that's outside of the region where we have these other temperature sensors, channels 2, 3, 4, and that's why here for about 20 seconds or so we don't see any change in temperature. But then after that, diffusion takes over, and this heat starts spreading, and then we start seeing a rise in temperature. So what it turns out to be is that in general, microwave ablation is happened by direct microwave heating and also diffusion. But at higher frequencies, the role of this diffusion is actually very important. But the net result is that regardless of the mechanism, at higher frequencies, microwave ablation actually happens both faster, and the size of the ablation zones that you end up with are pretty much comparable to the low frequency cases. So here we are looking at some sample photographs of the ablation zones that were created with these antennas at 1.9 gigahertz. And after the experiment was done, we actually cut the tissue, visually examined the ablation zone, and measured the dimensions of the ablation zone. And this is what we are looking at. So this is the size of the ablation zone at 1.9 gigahertz after 5 minutes. And photographs are shown here. These are from the 4 different experiments. And the long and short axis diameters, the long axis diameter being this dimension, the short axis diameter being that dimension, are shown here as well. Now, if you look at the same number for the 10 gigahertz case, you see exactly similar looking ablation zones and also similar ablation zone dimensions. So regardless of the mechanism, at the same time with the same total input power, the ablation zone dimensions that we get ended up being the same. So that was interesting because that sort of told us that, that at least in these ex vivo situations, using higher frequencies versus lower frequencies really it doesn't have any advantages, or using low frequencies over high frequencies. Now at higher frequencies our antennas get smaller, so that's an advantage that we're interested in exploiting. But these experiments were done in ex vivo situations, so we didn't have any of the cooling effects of blood perfusion that you normally have in living tissue. So the next thing that we had to do was to actually do these experiments in perfused tissue, because at these higher frequencies, as I mentioned, we have direct heating and diffusion is a process that can be impacted by blood perfusion. So what we did was to, we have a blood perfusion chamber in our lab, and we basically took our livers. These are now porcine livers because they're smaller and they actually fit in our perfusion chamber. And we put them in our perfusion chamber, and we have a pump that's sitting behind this perfusion chamber and is actually pumping in liquid. In this case, it's water that's kept at a constant temperature through these. And basically, in some experiments, we actually dyed the water to make sure that we can actually map out the regions in the liver that are perfused. And it turns out that if you make sure that the main arteries, you have water going into the main arteries, you get pretty uniform perfusion across the tissue. But other than the tissue being perfused, the experiments were pretty much the same. We had our RF signal generators, our power amplifiers, and we had our antennas, and we did ablation experiments in these perfused situations. And the antennas that we had in this case, we increased the number of frequencies that we used. We essentially, previously we had 1.9 gigahertz and 10 gigahertz, and this time we did our experiments at 1.9 gigahertz, 6, 10, 14, and 18 gigahertz. And the choices of these frequencies were, by the way, to a great extent impacted by the available power amplifiers that we have. So, but that covers a pretty wide range over the interested low and high microwave frequency bands. So this is a very interesting figure. This figure shows the 75% energy absorption counters for these different antennas that we designed. The antennas, their designs are the same as these FSDs. They have basically dipoles with floating sleeve chokes. And each of these contours show the volume within which 70% of the applied microwave energy is absorbed. And you can see that as frequency increases at 1.9 gigahertz, you have the largest volume, the wavelength is larger, so the electromagnetic waves penetrate deeper. At 6 gigahertz, it's smaller, and so on and so forth. So you get smaller and smaller regions within which the microwave energy is absorbed. In all of these experiments, we actually use the same amount of power. So, and we basically wanted to see if the ablation zone dimensions that we get end up being similar or not. So what we are looking at here are sample photographs of ablation experiments that are performed at different frequencies ranging from 1.9 gigahertz to 18 gigahertz for 5-minute ablation duration and at input power level of 25 watts. And in this case, in these tissues that you see, the perfusion was active. So we had cooling due to perfusion. And we also repeated the same experiments without perfusion, just to have a controlled case for comparing. And again, these are some sample ablation results for situations where we did not have ablations. Now, these are just sample photographs. Each of these experiments were repeated a number of times so that we can get some statistical sense of the dimensions. And one liver that you get from the other liver, the tissue is not exactly the same. The tissue is not completely homogeneous. So you have to repeat the experiments more than once in order to be able to make any meaningful conclusion out of the results that you get. Once the experiments were done, again, we cut the tissue and visually examine the ablation zone, measure the dimensions of the ablation zone, and we report these dimensions by reporting the long and short axis radii of the ablation. So in this case, RA and RB are the two dimensions, where 2 times RB is the dimension of the ablations along the long axis, and 2 times RA is the dimension along the short axis. So the results are actually tabulated here, and what we are looking at are the results for our simulations, for in vivo simulations, and our perfused experiments. So you see 3 different curves here. We have RA, RB, which are these 2 dimensions, the short and long axis radii, And the ratio of these, where the ratio actually tells you how close this ablation zone is to a spherical shape. And that is, in most situations, is generally desired to have a spherically shaped ablation zones. And so interestingly, we'll see that this ratio approaches 1 as frequency increases. And in general, we don't see significant differences between these dimensions as frequency increases. There is a slight decrease in dimensions of the RB along this direction as frequency increases, but the dimension along the other direction doesn't change that much. Our measurements, the error bars in our measurements are actually pretty large. Here we have a limited sample, I think about 5 experiments at each frequency, and that's why the error bars are pretty large. But again, if you look at the average RB values and RA values, the median values, they don't really change that much with frequency. And these are for situations where we actually have perfusion. So again, this kind of tells us that as frequency increases, even though at higher frequencies the ablation is performed by a combination of direct heating and perfusion, the cooling effects of diffusion, the cooling effects of blood perfusion don't significantly impact the size of the ablation zones that you get. Now these are experiments that we had and simulation experiments for the unperfused cases. And again, our prior finding was that for unperfused cases, as frequency changes, the dimensions of the ablation zone should not change. And again, we see similar trends here as well. So in terms of the, based on these measurement results, we also estimated the total volume of the ablation zone that you can get in the ex vivo and the in vivo cases. And again, we'll see that as frequency changes, the dimensions or the volumes of the ablation zones don't change that much. So what does that tell us? That basically tells us that using higher frequencies or lower frequencies, you can pretty much get whatever size of ablation zone that you want, and that you can control by applying by changing the applied power to the antenna that you're using for ablation. So this is true in case of ex vivo ablations and in vivo ablations. Now, going to higher frequencies, as I mentioned, allows us to make the antennas shorter, and that is desirable because it makes the antennas it actually enables us to use possibly flexible antennas that can be routed to the ablation zone, with true natural anatomical pathways in the body. But the next thing that we wanted to do was to make the antennas thinner as well. So if you remember, in one of the earlier slides, I showed that floating sleeve dipole antenna, and that antenna was a coaxial fed dipole antenna, but we had this balun, which was a third conductor that was covering the outer conductor of the coaxial cable there. And that was there to make sure that the currents that are flowing on the outer surface of the outer conductor of the antenna are actually choked. If these currents are not choked, then you'll have currents running along the length of your antenna, and those currents contribute to heating. And so what happens is that as you put this antenna into the tissue, this antenna passes through a bunch of healthy tissue and then arrives at the tumor, and you'll end up ablating the healthy tissue, which is not desired. So these antennas have to have some sort of a mechanism to choke these currents that are flowing in the outer surface of the outer conductors of the coaxial cables. And that's why we have this third conductor. But that third conductor increases the diameter of the antenna. So imagine that you're putting a needle into the body. If you have a thicker needle, it's not as desirable as having a thinner one. So in the second part, we look at antenna design concepts where we can actually reduce the thickness of these antennas and get rid of these baluns altogether. So what I'm showing here is a basic monopole antenna, coaxial cable-fed monopole antenna. In this case, the monopole is in the form of this helix, but it really doesn't matter. It can be a straight line as well. And what we're looking at here is the input reflection coefficient of this antenna as seen from this reference point. So For those of you who've taken antenna courses, you know that if I have a monopole antenna, if the length of the monopole is quarter wavelength, I can easily impedance match that antenna. If it's half a wavelength, then the current at this point goes to 0. I'll end up having a very high feed point impedance at that point, and it's not very easy to impedance match the antenna. So what we're looking at here is the input reflection coefficient of this antenna. At the first resonant frequency, where this electrical length is a quarter wavelength, you have pretty decent impedance match. At that second resonant frequency, where this electrical length is half a wavelength, you have a very high high feed point impedance, and you can't impedance match the antenna very easily. Now,
can I ask you a
yes,
question?
sir.
Why do you want to have even a radiating element? Why not just a capacitive element? Because anyway, the tissue is absorbing the near field of the antenna, not the radiating part.
Well, that's a good question. These are not radiating in the sense that our cell phone antennas are radiating. So everything happens in the near field. So we basically want to have an antenna with a good, decent impedance matching and a confined ablation, a confined SAR pattern, essentially.
Imagine that you have just a short dipole that is capacitive way below resonance frequency. And if I look at the near field, I establish electric field that generates heat. What's wrong with that?
There's nothing wrong with that. The problem is that you'll end up having a hard time impedance matching to that. And also,
why do I need even impedance matching? If I just need a voltage, it would be
well, I mean, your heating is done by the power that you put into the antenna, right?
But I can establish, let's say, a standing wave. I have a voltage, and
right.
that voltage takes in the power, and it absorbs by the resistive load.
Well, so actually we'll see a little bit of that here. We'll see a little bit of this concept here, and I think your question will be answered when we look at this. But the problem is that if there's any energy flowing to that, and if it's very, very electrically small, you'll end up running currents on your cable, and that will cause heating along the cable as well. So we'll see a little bit of that.
It is capacitive only. I don't have current.
Well, I mean, you have to have some way to heat this, right? So if it's completely capacitive, if you don't have any sort of resistance here, the power that you put into this will completely get reflected back. Now, what you're saying is true if you have capacitive there, you have a lossy tissue surrounding that, you'll draw current, but that means that you're actually putting current into the antenna, and that means that
have to go back on the other side.
Oh, it will. It will. So we'll actually see something similar to that in the next couple of slides, but it does. So all right. So so keep this in mind, this F1 and F2 thing in mind, and now let's look at the SAR patterns of this antenna. Now, what we are looking at here is the SAR pattern of the antenna. This is just the base-fed monopole antenna without any balun. And this is the SAR pattern at the first resonant frequency. And you can see that this negative 20 dB contours actually go right up to the air-liver interface. So this is where the point, this is the point that the antenna actually goes into the tissue here. And you can see that we are depositing energy all the way here. Now, going back to Professor Sarabandi's question, if you plot the SAR pattern of this antenna at frequencies way below the first resonant frequency, you actually get a very similar SAR pattern here. So at those frequencies, you have basically a capacitive element, but your SAR pattern is going to be very much similar to this. Interestingly, what we observed, again by accident, was as we were looking at the SAR pattern of the antenna, at the second resonant frequency, this is the frequency where the antenna is highly mismatched, we saw that the antenna has a very confined SAR pattern. So this was kind of like a natural choke point for the antenna where you're not using any balun, but you're getting a confined SAR pattern. Later on, we actually thought about that, and the reason ends up being that at the second resonant frequency, the feed point impedance of the antenna is very high. And what a balun is essentially that, is a mechanism for you to create a very high impedance point at the location where you want the currents to get suppressed, and the second resonant frequency of the antenna actually gives you that automatically. The problem, though, in this case is that it's highly impedance mismatched, so you cannot really deliver energy very efficiently to that, but that problem is one that has solution. So what you can do is you can actually, so the feed point impedance at this point is very high, but it's not infinite because we have a lossy tissue that's surrounding the antenna, so that brings down the feed point impedance a little bit. But the feed point impedance at this point is high, but all I need to do is to have an internal impedance matching network within my antenna. And what that does is that it converts that high feed point impedance from this point to 50 ohms there, but maintains the high feed point impedance there. So I will not have any current flowing on the other surface of my other conductor, but I actually can deliver energy very efficiently to the antenna. That was a very easy solution. And in this case, I'm showing a mechanism for implementing that impedance matching network with a quarter wavelength transformer. Turns out that it's hard to implement this in practice, so we ended up settling for a relatively easier method for implementing that internal impedance matching network, and that's basically implementing a pi impedance matching network here with two capacitors and an inductor, which are all implemented within the feeding transmission line. And you can go through the equations and you can show that you'll be able to get very good impedance matching in using both cases. So these are the simulations. At the first resonant frequency is what we don't care about. The second one, both using the pi network or the quarter wavelength impedance matching, we have pretty decent impedance matching, and both of these techniques give us pretty confined ablation zones. So these are pretty confined SAR patterns. So these are, again, without using any third conductor surrounding the antenna. So we went and fabricated a prototype of this antenna. We measured it. It actually works pretty well, and used that to perform ablation experiments. And these are two ablation experiments that we did at 1.9 gigahertz with the same power levels, 42 watts, as the ones that I showed a little bit earlier. And as you can see, the ablation zones, as expected, are confined. We don't have any heating along the cable. So this basically shows that the antenna provides a very confined SAR pattern and a very confined heating zone without using these external balun. So in this antenna, one challenge was to actually implement this internal impedance matching network that I showed. It's a little bit hard to fabricate. Another challenge, which can be an opportunity for some other applications, is that the bandwidth of the antenna is actually pretty narrow over the frequency that we get good impedance matching. So what one of my students did was he actually came up with an even simpler idea of doing a similar thing, but without having a structure that has these bandwidth limitations. And basically, the idea here was simple: was that rather than using these coaxial balance, why don't we create some sort of a transition between our coaxial cable, which is an unbalanced transmission line, to a two-wire transmission line, which is a balanced transmission line. And if we use this two-wire transmission line to feed our antenna, we don't need an external coaxial balun, and we can still get pretty thin antennas for microwave ablation. So the concept is actually shown here. So what we have here is a coaxial cable that is transitioning by tapering this outer conductor of the coaxial cable, the shape of this outer conductor of the coaxial cable, to a two-wire transmission line at this end. And at that end, we basically have a differentially fed structure if we take our output from these two conductors. So the tapered outer conductor of the coaxial cable and the center conductor as before. So based on that, you can actually design an antenna in two different ways. One way is shown here, where we have our tapered outer conductor of the coaxial cable. We extend the inner conductor a little bit, so that creates one of the dipole arms, and then we connect a section of metal here to form the second conductor of the dipole antenna. So we'll have basically a dipole antenna where one arm is this conductor, the other arm is that one. So this is sort of the outer conductor of the coaxial cable rolled in flat, so that you can see exactly how it looks like. Now, this structure works, but it turns out to generate heating patterns that are slightly asymmetric. So to improve the symmetry, he then came up with this idea of basically balancing, using two conductors for the second arm of the dipole. So here, our antenna actually has three conductors. This would be one of the arms of the dipole, and these two conductors are the other arms of the dipole. But the idea is essentially the same, transition from an unbalanced to a balanced transmission line, all within one single coaxial cable. And it turns out that these sort of transitions, you can design them to be pretty broadband, so we don't have the same limitations that we had in the previous case. And in this case, we are looking at the input VSWR of one of these antennas that's designed to work around 6 gigahertz or so. You can see that it's a pretty broadband structure. If you look at the SAR pattern of the antenna, this is the SAR pattern of that antenna that has only two conductors, one arm for each of the or one metal section for each of the arms of the dipole, you can see that because this structure is asymmetric, the SAR pattern of the antenna in one of the planes can be asymmetric, and that can result in asymmetric ablation zone. So these are thermal simulation results, and they show that the ablation zone is slightly asymmetric. And if that is not desired, if you do want to have a symmetric ablation zone, then what you can do is use the second type of structure that I showed. And in that case, the structure has symmetric SAR patterns and heating patterns in both principal cuts along the longitudinal axis of the dipole. So simulation results of this show that we have very symmetric heating pattern, rotational symmetric, despite the shape of the antenna. Now we fabricated a prototype of this antenna. This one looks a little bit more intricate, but there are companies that can do laser etching of cylindrical conductors. So what you see is one section of the outer conductor of the coaxial cable that this company for us fabricated with laser etching. It's working very nicely. So it's just a copper tube that they remove part of the surface to get the profile that we want. And then we got our coaxial cable and then passed that through this after stripping out some of the outer conductor of the coaxial cable. So the measurement results of this antenna actually show pretty good impedance matching, wideband impedance matching, similar to the simulation results. And we also did experiments with this antenna, performed ablation experiments at different power levels and for different durations in bovine liver. And again, we see very confined ablation zones, rotationally symmetric ablation zones in two different planes, XZ and YZ planes. And interestingly, in this structure, the ablation zone that the antenna produces is very close to a spherical. So if you look at the ablation, the aspect ratio of the ablation zone is about 1.3 or so, 1 indicating a perfect sphere. And in the published literature, that's actually one of the lowest aspect ratios. So this ablation zone that this antenna provides is pretty much closest to a spherical as any antenna gets. So let me summarize this talk here. So what we have done here, we have basically, in this work, we have shown that it's feasible to use high frequencies, high micro frequencies to perform microwave ablation. We have shown that this is valid for both ex vivo and in vivo cases. And we also have come up with ideas for reducing the thickness of these ablation antennas that you're using. So the idea is that by going to higher frequencies, you can make the antennas shorter. And by using one of these designs, you can make them thinner. And so you'll have antennas that can potentially be less invasive compared to other antennas. So we've done other activities in this area as well that I haven't had a chance to go over, but we have antennas that can generate directional heating patterns. This is a photograph of an experiment of such antenna that basically directs heat towards a specific direction within the body. And we've done some preclinical studies of doing microwave ablation in excised breast tissue. And for our future work in this area will be looking into flexible antennas. Now that we can have short and thin antennas, can we make them flexible and route them perhaps through veins, to certain parts of the body that we need to perform ablation? So a lot of interesting things to come, but I'll stop the presentation at this point, and I'll thank you very much for your attention, and I'll be happy to answer any questions that you may have. Thank you.
But it was George who was the prover, along with Kenshin, of the ergodic theorem. So he was both involved in probability and in symbolic logic, which was an interesting combination.